This is a demonstration of the Spirent TestCenter feature for PGA, Packet Generator Analyzer. I'm going to start with the Spirent TestCenter application open and dismiss the welcome screen. I'm going to go straight to Connect Chassis and Reserve Ports. From there, I'm going to connect to a specific chassis. In this case, I'm going to be using the first two ports on slot 1. Once I've reserved the ports, you'll notice that they appear on the test configuration screen, and I'm going to build my configuration from top to bottom. I'm going to start with all ports, make sure my media type is set appropriately, go to the Port Config tab, set my physical layer. In this case, my device under test is running at 100 meg full duplex. Next, I'm going to create some traffic endpoints. For that, I'm going to create a device on each port. So I'm going to select all devices and access the Create Devices wizard. I'm going to select both ports. In this case, I'm going to be creating traffic only devices. For the encapsulation, it's IP version 4 only. I'm not including any VLAN tags. I'm only going to create one device per port, so I'll have something to select as a traffic endpoint. I'm going to leave the default MAC address, but be careful that you don't duplicate those. My device under test is configured with the following subnets: 192, 168, 11, and I'm going to give my device for Spirent TestCenter the value of .2. The gateways will default to .1, and that is what they need to be for my circumstance. I need to make sure that I set up the port step for the IP address appropriately. Since we're using a /24 prefix, the port step should be 0.0.1.0. I'm going to go ahead and launch the traffic wizard automatically from here when I'm done. I can preview both my MAC addresses and my IP addresses and my gateway to make sure that they are appropriate. They are for the environment that I'm testing in today. Once I've finished the device wizard, I check the box to automatically launch the traffic wizard. From there, I'm going to use both ports. And notice how the devices on those ports show up as traffic endpoints. So I'm going to add a pair. And I'm going to make the traffic bidirectional. So now I'll have traffic flowing in both directions. There's a variety of ways that I can set up the frame size. A fixed frame size. I can set up a random minimum maximum value. For this example, I'm going to set it to increment, and I'm going to set the minimum frame size to 64, which is the smallest legal Ethernet frame size, the maximum frame size to 1518, which is the largest maximum size frame size without VLAN tags and not running jumbo frames. I'm going to leave the step at 1, so essentially that means that as I transmit traffic from this stream block, we're going to be sending every legal frame size, 64, 65, 66, up to 1518, and then cycle back to 64. I'm going to do that on purpose because I want you to see how the generator can aggregate all those values into a single traffic stream. The analyzer can analyze them as an aggregate value, but then it could also break them out. The stream block name prefix is arbitrary. I'm just going to leave it as stream block. I'm not going to add any other information to the frame. I could add a TCP or a UDP header to the stream block frame, keeping in mind that the frame and IP headers are coming from the associated device endpoints already. I'm using a port load rather than a load per stream block, but in this case, if I'm only generating one stream block per port, it's not going to matter much between the two. The load can be changed. I'm just going to leave it at 10% for this example. And I'm going to finish. So now you can see I have my two devices, their associated MAC and IP information. I have my two stream blocks, one on port 1 and the other on port 2. And you can see it's a port pair and the transmit and receive ports respectively. So essentially I'm completed my configuration. So I'm going to go ahead and apply. The first time you apply, it may take a little longer because we're transferring all the configuration parameters from the GUI to begin with to the hardware. Subsequent applies will only transfer the changes. But as you can see in the status bar in the lower right, it's already done. Now I could save my configuration from here, and it will save it as a .tcc file, which is probably a good idea, especially if you set up a large test to begin with. Next thing I want to do is resolve my MAC addresses for my gateways. So I'm going to use the Start ARP-ND button from the toolbar. And as you can see in the bottom left-hand corner of the app, all ARPs resolved successfully. We could even scroll over in either the stream block and see that the ARP status is resolved, or the devices, and we could also see not only that the status is resolved, but also the gateway's MAC that was configured accordingly. So the idea of bound stream blocks is whatever MAC address is resolved for the gateway will automatically be used for the traffic in that stream block. So now I'm ready to start my test. But before I do, I'm going to pull up my result window, and I'm going to pin it up so it will be persistent. And you can see that we've sent and received some packets already. Those were the ARP exchanges. I'm going to go ahead and clear all my result views. So that way I'm starting my test with clear counters. Now I can start my test in a variety of ways. I can right click on the generators and start all the traffic for that generator. I can right click on a stream block and start just that one stream block. Or I can start everything by using the Start Traffic on All ports from the toolbar, which is what I'm going to do. Now at first glance everything seems to be working. I'm getting traffic through at the aggregate port level, and then if I look at my stream level, I can see my transmit and receive ports for each stream broken out separately. And so far everything looks good. I can scroll over from my detailed stream results, basic counters, and there I'll find my latency information. I could change to my sequencing tab, and there I'm going to find whether or not I'm dropping any frames. So the advanced sequence tracking algorithm is keeping track of the sequence and frames in real time. So we're not dropping any frames yet, and that's good. But remember earlier we set this up where we're transmitting every legal frame size. How do we know that? How do we know that the traffic associated with each one of these stream blocks is generating every legal frame size? The generator's aggregating those all into the single statistic, and right now the analyzer's tracking them all as a single statistic. Well, what if I had dropped some frames? We're going to set up analyzer filters next. And the analyzer filters are going to give us a chance to filter the traffic not by the stream ID, as we have depicted here, which is the default for the analyzer filters, 32-bit filter over stream ID, but by something else in the frame that's going to give us a clue as to what the frame sizes are. Before I change my analyzer filters, I'm going to stop my traffic because they're going to have to reinitialize anyway. Now that I've done that, I'm going to drag down the results window here so I have some more room to work with on the traffic analyzer filters, the template filters. Now, if you think about it, we have an Ethernet version 2 frame with an IP header. Where can we view what the length of the packet is? We can't use the Ethernet header for that because it has a type field as opposed to 802.3, which has a length field, which would allow us to do that. But rather, we can go inside the IP header and select the total length field. But keeping in mind that this is the IP total length, so it's only the IP header and the payload, but not the Ethernet header. So a minimum size 64-byte Ethernet frame would actually translate to a 46-byte IP. Similar, a maximum size Ethernet frame of 1518 would actually translate to an IP total length of 1500. Now, I can change both analyzers, and it might be recommended to do so you have the same thing on both ports, but it's not actually a requirement to do so because Spirent TestCenter allows different analyzer filters on different ports. For now, we'll just look at things on port 1 by changing the analyzer filters there. So I'm going to go ahead and apply that configuration. And I'm going to bring my results back up. Just so I can see more things at once, I'm going to change my results view to a 1x1 layout. Key thing to remember is when you have changed the analyzer default filters, you no longer want to view the detailed stream results, because that will include the transmit frames only. Rather, we need to look at it from strictly a receive perspective, keeping in mind that different ports can receive different types of traffic based on their filters. So I'm going to change to filtered streams results. And when I do so, you'll notice now I select the results by port, because again, each port can have a different filter, which in this case they do. Port 1 now has an analyzer filter based on the stream ID and the IP total length, whereas port 2 still has just the default filter set on the stream ID. So far, nothing has been collected because I haven't received anything. So I'm going to go ahead and start my traffic. And right away you can see we're already receiving frames. But now, instead of one record, we have multiple records. Notice that the first record is IP total length 46, which is equal to Ethernet frame length 64. Now, each page only has 25 entries. Because keep in mind that whenever we change a result view, we're subscribing to those statistics. You'll notice that there's 59 pages of up to 25 streams, which is over 1,400 streams, which is what we would expect if we're receiving frames from 64 bytes up to 1518 or IP total length 46 up to 1,500. So because we started transmitting and we had our analyzer filters cleared, we received the first minimum size frame. We can scroll to the last page. Notice that the last frame is 1,500 bytes. One thing I'll point out is that we are actually receiving frames that the generator aggregated into one stream. Notice that they all have the same stream ID, and the statistics are valid. Notice latency, statistics. But the problem is, since it was one stream, if we look at our sequence tracking, it thinks it's dropping a lot of frames. Keep in mind that one stream is generating sequences 1, 2, 3, 4, 5. Sequence 1 is now received on the first record, sequence 2 on the second, sequence 3 on the third, all the way up to the last record on page 59, which is our 1,500 byte frame, which then it cycles back to our first frame, which had skipped some 1,400 plus values. So let's say it was 1,400. The first record received sequence 1, and then it received sequence 1,401. So from a sequence tracking perspective, we think we dropped a lot of frames. So that's just something to keep in mind. Whenever the generator and analyzer don't match, whether the generator's aggregating things together like it is here and the analyzer's breaking them out, you end up with drop frames. Conversely, if the generator was breaking them out and then the analyzer was aggregating them together, then you would have the frames showing a lot of duplicate counts, because you would actually receive sequence 111, 222, 333 that were generated by separate streams and now aggregated all into one statistic. That completes this demonstration of Spirent TestCenter PGA.